Welcome! Let's take a look at using the fundamental theorem of calculus to help us evaluate some definite integrals. Our first example here is the integral from 0 to 4 of 3x squared dx. Let's remind ourselves the fundamental theorem of calculus tells us that if f of x is continuous on the closed interval from a to b, then the definite integral from a to b of f of x dx is equal to capital F at b minus capital F at a, where f of x is any antiderivative of f of x. And the connection between the antiderivative and the integrand is that the derivative of the antiderivative must equal the integrand. So let's take a look at our first example here. Now, our integrand is 3x squared, and what we need to do is identify the an antiderivative. So that is, what function can I take the derivative of? And when I take that derivative, I get 3x squared. Well, some people will look at 3x squared and immediately recognize that if they take the derivative of x cubed, they will arrive at 3x squared. While others may not make that immediate connection. So others may think, well, the derivative was found here via the power rule, so I'm going to try to undo the power rule. So they may think of this as f of x, my antiderivative, must be 3 times, and now I'm going to focus my attention on x squared. I know that I took a derivative, and when I did that, I subtracted 1 from the exponent. So I'm going to add 1 back into the exponent. And then I know that whatever this new exponent is, I need to multiply by 1 over that new value. And at this point, they would recognize that they have 3 times 1 over 3. So those would divide out, and we would end up with our antiderivative being x cubed. And then they could, of course, confirm that the derivative of that is the integrand that they have in this particular integral. So with that in mind, and knowing that our antiderivative is x cubed, we have x cubed, and we need to evaluate that between x equals 0 and x equals 4. So substituting x equals 4 into our antiderivative, we get 4 cubed, minus, and then substituting 0 into our antiderivative, we get 0 cubed. 4 cubed is 64, minus 0 cubed, so we would simply end up with 64 as the value of our antiderivative. Now looking at our second example here, notice that we have a series of terms. We can use properties of integrals to help us kind of focus on each term individually. And what I mean by this is that I can look at this as negative 1/2 times the integral from 0 to 3 of x squared plus 2 times the integral from 0 to 3 of x plus 2 times the integral from 0 to 3 of 1. And I'm missing my, there we go, differential on all of those, dx. And so this allows me to focus on integrating term by term. And for many, this can become or this can help a problem become less overwhelming. So let's go ahead and integrate here. And we'll need to find the antiderivative for each of our integrands. So we would end up with -1/2 times, and now the antiderivative of x squared. Notice that for all of these, basically we're dealing with the power rule. So x squared is what my integrand is. So that means when I was taking the derivative, I subtracted 1 from the exponent. So we will add 1 back in. And then I need to multiply by 1 over that exponent. So that when I take this derivative, I end up with x squared. And so 1/3 x cubed has a derivative of x squared. And we will evaluate that from x equals 0 to x equals 3. Plus our next term at 2 times. And now the antiderivative of x. The exponent here is 1, so similar process. Current exponent is 1, and derivative was obtained via the power rule. So subtracting 1, we need to add 1 back in, and then need to multiply by 1 over that exponent. And notice we have x squared, and so the derivative of 1/2 x squared will in fact give us x. And we want to evaluate that between x equals 0 and x equals 3. Plus 2 times. Now, the antiderivative of 1 is x. Recall that if you took the derivative of x, you would end up with 1. So the antiderivative here is x. And we would evaluate between x equals 0 and x equals 3. Now notice that for each of these terms, I'm evaluating between the same limits of integration. So rather than separate them like this, I could just as well look at this as -1/2 times 1/3 x cubed plus, let's see, 2 times 1/2 is 1, so x squared plus 2x, and then take that longer expression and evaluate that between x equals 0 and x equals 3. So either is fine. So let's go ahead and evaluate. So we're going to substitute into our antiderivative x equals 3 first. So -1/2 times -1/3. I'm going to actually leave that as -1/2 times 1/3. And when I evaluate that at 3, I get times 3 cubed plus 3 squared plus 2 times 3 minus, and then evaluating this same antiderivative at 0, I get 0 plus 0 plus 0. 0 times -1/6 is 0, 0 squared is 0, and 2 times 0 is 0. Now, the reason I didn't multiply the -1/2 and the 1/3 is I noticed that this 3 in the denominator can simplify with one of the 3's in my 3 cubed. So this can become, instead of 1/3 times 3 cubed, it can just become a 3 squared. So then, now we have -9/2 plus 9 plus 6. And let's get a common denominator of 2. So -9/2, 9 is 18/2, and 6 is 12/2. And with that common denominator, I have positive 30 halves minus 9 halves. So positive 30 minus 9 is positive 21 halves is the value of this definite integral. I hope you find this helpful.